Okay, welcome back. Let's carry on to our second sections. Okay, so I started recording. Okay, next we proceed to section 5.4, the central limit theorems. Okay, for this chapter, so we have another two sections. So the first one, 5.4, so this will be central limit theorems. And 5.5, so that will be a law of large number. So these two, we can say that these two can be considered as the most important result in maybe we can say statistical analysis. Okay, right. So because these two happens to be, I think you guys have already know what the statement for this. So we can apply these two results to get the approximations to estimate, okay, or we can get the approximation to estimate. So the parameters of given populations, okay, something like that, okay, of large size. So theoretic, so we go to the theory for these two results. So basically, we will study this. What conditions need to be fulfilled, okay, before applying these two okay, what condition we're going to look at this topics. What condition need to be fulfilled before applying these two results? Okay. Okay, maybe we look at the first one, central limit theorem first. So to discuss about this central limit theorems, okay, maybe we need some, just look at some fix some symbols over here. Okay, so first we just assume this to make things easy. So we assume, okay, maybe we solve this. So here's the statements for it. Okay, so let's say we have a sequence, given a sequence of random variable x1, x2, x3, and so on. So what we'll do? Okay, first we make such assumptions. We assume all these random variables are having zero mean. So it doesn't really matter. We normalize this just to makes our formula looks easier. So what we can do is when mean is not zero, so when the mean for xi is not zero, so we can consider xi minus the mean of it. Okay. If we consider this, then we can see this new random variable we're going to have a zero mean. So that's why it doesn't really matter. We want to put it this or not. Okay. So we make this is actually just to simplify the formula for it. Okay. Next, we're going to use this standard notation. So we just simply write Sn to be so summating all the xi, I running from 1 to n. So these are the symbols that we're going to use throughout the sections here. And also we write this sigma n to be the variance of Sn. Okay. So because of the E of xi is 0, so that means automatically we're going to have the mean of Sn will be 0. So this one is because of this will automatically implies this thing. Okay, now we want to know this. So this is what we so-called the center limit theorem. So Sn over sigma n. In fact, it's sort of like we have to minus the main for it. Okay. Converge to standard normal distributions in distributions. Okay, so then we have that. For what condition here, then we can have this situation. And this one, this is what we so-called the center limit. We just simply call it center limit theorems. So we're going to look at here. Under what situations we can see that Sn, because this new sequence of random variable Sn over sigma n will converge in distribution to the standard normal distribution. So this is what we're going to discuss in sections 5.3. Okay. So in these chapters, in this section, we're going to discuss several versions for this center limit theorems, as well as some of the examples. Okay, so before this, let's look at the summary for the sections over here. Okay, maybe just look at the first two. Okay, so I have already posted this summary in the Spectrum, so you guys can go and download it on yourself later. All right. Okay. So this is a supplement for chapter 5B. So I just list out those are important results and important result in these sections. Okay. Okay. So let's look at here. Okay, let's look at our setting. First, supposing we have a sequence of random variable x1, x2, x3, and so on. So we always assume these two conditions. First of all, we always assume this sequence of random variable are all independent. Okay, and secondly, we assume E of xi is equals to 0. Okay, like I said, if E of xi is not 0, we may replace it with some other random variable. Okay, so this is just to simplify our formula. So this is a notation. We just simplify Sn to be summating xi, and we use a shorthand sigma n squared to represent the variance of Sn. Okay, so we're going to consider 6 conditions. Okay, 6 of them. Basically, and then 2 of them are conclusion, the other 4 are hypothesis. Okay, 6 of them. So which are, look at these 6 here. So the first one, Lindemann conditions. So this is the one. Okay, we're going to look at later. And the next one, Lyapunov conditions. This one, and IID. So independence and identical distributed conditions. So this one just means x1, x2, x3 are all independent and having the same distribution. We just simply write variance of xi to be sigma squared. Right, so this is the condition. Center limits theorem condition, that is Sn over sigma n converge in distribution to the standard normal distributions. Okay. And 5 and 6 we're going to discuss in the next sections. So the weak law of large number and the strong law of large number. So this we leave it first. So just look at this. Okay, before we go into the details, so let's look at the relationship for this. So it's in the next page. I hope you can get a picture here. So like I said, what we want is we want to get this conclusion, center limit theorems, or we want to get this conclusion, strong law of large number or weak law of large number. So that is, we want to know under what situations or hypothesis can lead us to such a conclusion, right? Of course, we do have a lot of versions of center limit theorem. Here, we only discuss those, the classical one or the most simple one. Okay, okay, so we have several versions. Okay, first we have the relationship between this Lyapunov condition and Lindenberg condition. So if the variance of xi is always finite with a Lyapunov condition, so this always implies Lindenberg. So if it satisfies the Lyapunov condition, so then it's always satisfy the Lindenberg conditions. Okay. So we're going to look at these two conditions. What are these two conditions later, right? Okay, next. So we have two versions of center limit theorems. So the first one is Lindenberg revised center limit theorem. That is, if the sequence of random variables satisfy this, they are independent and identically having identical distribution, then we can lead to this conclusion, center limit theorem's conclusions. So this is theorem 5.4.1. Alternately, we also can have this. So this is the Lindenberg's center limit condition. If the random variable sequence of random variable xi satisfy the Lindenberg condition, so we can also have this conclusion, center limit theorem. So in fact, this condition is stronger than this. Okay, that means if the random variable is identical and independent, then it's always satisfy the Lindenberg condition. So at least for section 5.3, so these are the relationship for this. Okay, so please remember this. Okay, you can see now you can see when you can apply this center limit theorem. So that is when we can apply the center limit theorems. Okay, so case one. So of course we do have several cases. So I mean, what I'm talking about is in our contents here, okay, under our chapter here. Case one, when XIR IID. So independence and okay, clear? Okay, better. So when they are independent and having the same distributions, okay, so then we can have this. So this is the one. So first case, we can have this. Okay, similarly, the second case. So case two, okay. So when xi satisfy Lindenberg conditions. Okay, so it satisfies the Lindeberg condition, but it might not have having the same distributions. Okay, so then we also have this. So here we discussed two different cases for it. So one is the Lindeberg condition, the other one is the independence and identical distributions. Okay. All right. So so these are the topics that we're going to discuss today. Okay. So let's proceed to our chapter. Yeah, we just discuss it one by one. So again, okay, so okay, all these are actually I just copy from our lecture notes here, so you may refer it. So this is actually in our page. This is in page 7, just to let you know about this. Okay, if you want to know. Okay, so this is section 5.4. So we start with section 5.4. Okay, page 7. Okay. So again, as I said, we always assume this and we use these notations. Okay. First of all, we assume our sequence of xi is independent, right? First of all, we always assume they are independent. Secondly, we set e of xi to be 0. Okay. So when e of xi is not 0, so we can consider xi minus mu I instead of xi. So then we will get back to these conditions, right? Next, we take Sn to be this. Okay, we just simply write this notation, and this is a sigma. So this is our assumption, right? So maybe just to explain to you what is it. So that is when e of xi equals to mu I, that is not necessarily 0. So what we can do is, so we just simply write y of I to be xi minus mu of I. Okay, so then we can see e of xi will be equal to 0. So that's why automatically we have these conditions. Okay, and also then we just consider, then we do the analysis, we study Sn that is equal to summating yi instead of xi. Okay, we are taking Si to be this. Then we just apply our result, our theorem to yi instead of xi. Right? So that is the idea for it. So since we can always do such a conversions, so that's why what we can express our formula in a relatively easiest form. That is, we just simply the mean of the all random variable xi will be equals to 0. Okay. So we have this. So we always make such assumptions. Then first theorems will be this. Okay. So you may refer to the textbooks. Sorry, the lecture notes. So this is a theorem 5.4.1. So this is a Lindeberg revised center limits theorems. Okay, I think maybe I put it in this way. That would be better, so that you can see it. Yeah, I will write it down instead of cut from our lecture notes. Okay, so please you may refer to the lecture notes. Okay, so I will assume this. So what are the hypotheses? Okay, suppose first of all, x1, x2 x3 are independent and having the same distributions. Okay, and also we assume E of xi to be 0. Okay, so this is not important. Just to simplify our formula. Okay, number 3, we assume the variance of xi, we use a notation sigma, which is not infinity and greater than 0. Yeah, of course, we need this kind of symbol. So at the same time, we're going to use this symbol Sn to be summating all the xi, I running from 1 to n. We just simply write sigma n to be variance of Sn. So which is equals to, so in this case, we can see sigma n will be n of them, okay, n of sigma square. Okay, a special case. Okay, so we have A, B, C. Okay, suppose this, then we have this conclusion. Then we're going to have Sn over sigma n. So since we have, this is a square. So because of this, then we can have more detailed information. Sn over sigma square of n. This will converge to the standard normal distribution in distribution. So this is the first version of our central limit theorem, LLCLT. The Lindeberg revised central limit theorems. Okay, so this is very easy to use. Before applying these theorems, we just need to verify one condition. Okay, as long as these are independent and having the same distributions, and B and C, of course, we want to make sure the standard deviation or variance are finite positive numbers. Okay, then we're going to have these conclusions. Right, so next, before we proceed to an example, so just look at the remarks here. Okay, so as I said, the second condition B here, E of xi is 0, is not necessarily, we put it there just because of we want to simplify our formula. Okay, so in general, if E of xi is not 0, then the mean for Sn will be n mu. So we may replace the formula with this. So that means what we need to do is we just add in an extra terms over here. Okay. Okay. So let's carry on to our examples. So first we have an example. The first example. So we have a ABC. Okay, A. Okay, so we have assume xi are IID. Okay, and also we said that all the xi follow the binomial distributions with n equals to 1 and probability of success is 1. So this is the thing. Okay, so we have this already. So IID satisfied, then we can apply the central limit theorem. So in this case, because of xi is having a binomial distributions, so by using the standard formula, then we know by the table, then we can see this E of x, E of x, right? Okay, maybe you can put mu equals to E of xi because all of them are having the same distribution. So which is equals to n, okay. Because of p equals to 1, so which is equals to p and the variance is equal to NPQ or PQ. So sigma, this is a sigma square. This. So then what we can do is we can apply this formula directly. Okay, so hence we can see we can have a Sn minus, using this formula, it's supposed to be a n mu over sigma square of n. So if I plug in all this, so that will be just equals to Sn minus np over square of pqn. So this will converge in distribution to the standard normal distribution. So we can apply directly by the first version of center limit theorems. Okay, so let's look at case B. So again, in this case, we also consider independent and identical distributions. So that is all the xi are having chi-square with k equals to 1. So again, what we need to do is we can refer to the formula from the table. I can't remember what's the formula. So just refer to the table. Then you can see if for chi-square distribution, so the mean will be just equals to k. So in our case, that is equals to 1, and the variance sigma square is 2k. So in our case, that is equals to 2. So then we applying the same formula here. Okay, Sn minus n mu over this will converge to the standard normal distributions in distribution. So we can have, in this case, Sn minus, again, n mu and sigma square of n sigma. So that is Sn. So in our case, that will be minus n. So this is 2. So square of 2 multiplied n. So this will converge to standard normal distribution in distribution. So again, we can just directly by the first version of our central limit theorem. So actually, we just need to consider these conditions and make sure this is neither 0 nor infinity. Okay. So, and I think the third C is straightforward. So I not so C, I think this is straightforward. So you read the lecture notes, okay? Yeah, so this is one simple example, right? So if you refer back to the hypothesis for this first version of center limit theorems, in this Lindeberg revised center limit theorem. So we assume the hypothesis is all xi are having the same distributions. Okay, having the same distributions. So then we look at here, what happens when xi are not from the same distribution. Okay, what happens when xi are not from the same distribution? So in this case, which hypothesis we shall use? Okay, so this is the case. Okay, next, because this is quite common, right? When we consider random variable, the sequence of random variable, it might not come from the same distributions. Okay, it might come from different distributions. So if we have that scenario, what can we do? Okay, if we want, what hypothesis we should consider in order to lead to the central limit theorem. Okay. So one of the conditions that we can study will be this so-called the Lindbergh conditions. Okay, so maybe I will just write now. So this is in definition 5.4.3. So, however, this condition looks a bit scary. All right, this is so-called the Lindbergh conditions. Again, supposing we have a sequence of random variable xi, I running from 1, 2, 3, and so on. Okay, again, we use a simplified versions. E of xi is 0. Okay, with finite, what do you call it? Finite variance. Okay, this is just to ensure this is not 0. So we said that this xi satisfies the Lindbergh condition if and only if this is equals to 0 for every epsilon greater than 0. So again, when E of xi not equal to 0, so what happens? So when E of xi, so let's say equals to mu I is not 0. So what we can do is we just rephrase. We just rephrase this condition 5.4.1 as this. So we just add this minus mu I. Okay, we just sort of like replace xi with xi minus mu I, and then the rest will be remain the same. Okay. Okay, however, as I said, we can always consider xi to be 0. Otherwise, we can replace xi with xi minus mu I. So that's why we can always stick to these conditions. Okay, so this is one of the alternative that we can consider, the Lindbergh conditions. Okay, before we proceed to another version of the central limit theorems, so just look at this statement. Okay. Okay. IID always implies Lindbergh conditions. Okay, IID conditions always implies Lindbergh conditions. Okay, so as we have discussed in the earlier lecture, so which means what whatever conclusion arises from these Lindeberg conditions holds for independence and identical distributions. Okay, so this is one. Right, so this is actually the next example. So example 5.4.4. Okay. Right, so let's look at these examples. So example 5.4.4. So the sequence xi in theorem 5.4.1 satisfy the Lindeberg conditions. Okay. So that is what we want to prove. Okay, now we prove it, how to do it. So what we need to do it, we just substitute sigma n squared to be n sigma squared in 5.4.1. And then for each epsilon greater than 0, then we have this. So maybe we just look at it one by one. Okay, just look at the first line. Here. Okay, I think the first line, first equality is quite straightforward. Since we have this sigma n squared is equal to n sigma square. Okay, so we just substitute this into here, and which is independent of I, so we can take it out. Okay, this is how we can get it. So this is actually sigma n square. Yep. And also this sigma n square we can replace with n sigma square, so we can bring it over there. So this is how we can get the first line. Okay, straightforward from here. Okay, next here. So how to get this? The reason is here because of xi or iid, they are having the same distributions. Okay, so that's why the main of this must be the same. So this to this is because of they are having the same distributions. So then you have n of them. Okay, so that's why this is n. So you get cancel off, you get 1. So this is maybe we can just explain to you how to get this. So it's sort of like you have a 1 over n of e of x 1. Okay, I just put 1 plus e of x2 okay. And so here these are all together n times, and they are all the same. Okay, so they are all the same, equal to each other. And so that's why that means you cancel off n times, so you can cancel with this n. So that's why the remaining will be the first one. So this is how we can get it. Okay. So next, we just need to look at this expectation value. So this is actually a sequence of the expectation value of a new sequence of random variable. So this will converge to 0. So why this is converged to 0? Okay, so maybe we can look into this here. Okay, now let's explain this. Why this is equal to 0. Limit of n to infinity of e of x squared is equal to 0. Okay, so why this is 0? Okay, so we can go into the detail. Okay, to make it easy, what we can do is we can just simply write this. Let's say yn to be this. So since this is a running index n there, so we can simplify, write this to be our, okay, maybe instead of yn, zn. So we have a new, okay, maybe you want to make it easy. So what we can do is we can write this one as an. Okay. So here I use an to be this. Okay, I just simply construct a new sequence of random variable zn. So that is to represent it. Okay, if we write this, then we can see this. Then we have this. This zn is always smaller than x squared. Okay, right? Modulus of xn always smaller than x squared because this is a one indicator function here, and also e of x squared is equal to sigma squared, which is not equal to 0. So the first hypothesis, and the second hypothesis will be this. Again, this is the same idea. So you can see A1 is actually a decreasing sequence of event. Okay, if this is a decreasing sequence event with this, if you take the intersection of all of them, so this will be empty set. Okay, so this will be equals to empty set. So when not empty, okay, not empty. Maybe I think I should have said this is empty. Okay, so this is just equals to x taking infinity value. Okay, and because of e of xi is finite, which is not infinity, so then we can have this thing. The probability will be equal to 0. Okay, so for this one, so since we have this e of xi is not infinity, we must have p of this must be 0. So that means this thing is having 0 probability. Okay, we have this. So since this is a decreasing with this, then C, and we can see limit of yn will be equals to x squared. So limit of this, so 1 of intersection of these things. So we have this. Okay, now we come to here. We just simply say this is y. Okay, so this is y. Okay, now we have these conditions. Oh, sorry, not y. I have changed to z already. Okay, okay, so we just come back to So you just by using this Lebesgue dominant convergence theorems. We just write down statements.
Sorry, doctor, I want to ask something.
Yeah.
I want to ask the intersection of the AN, right? Does it equals to the, how to say, A infinity, where N is equals to infinity, something like that?
In a way, you may say this because of this is a decreasing case. When it is not a decreasing case, so you cannot say that. You get my point?
Yeah. So so the notation that written on that infinity equals to x, does it mean like what I understand just now?
Yes, but provided this is true, your interpretation is correct, provided this is true, because of this is a decreasing cases. Okay. Because this is a decreasing case. Yeah. Then you may interpret this one as a infinity. You may interpret in that way, but in general, that's not true. Let's say it could be up, be suddenly larger, smaller, larger, smaller. Then you might not have this case anymore, right? Okay. Actually, you can look at here. You can look at here. So because this is a keep on increasing, so again, as you see, you may follow the way you draw the line. So you can see this is actually getting smaller and smaller. So at the end of the day, so because when n approaches to infinity, so this is the only possibility will be x. The value of x is infinity. Okay. So this.
Okay.
Okay.
Okay. Thank you.
No problem. Sorry. I think because of okay, maybe just to write down this. What is this? What are we going to use? Okay, actually we are using this theorem 4.3.3. That will be easiest for you. Okay, so you may refer back to a result in theorem chapter 4, another important result, Lebesgue dominant convergence theorems. Okay, so let's say you have a sequence of random variable with finite mean. Okay, and if you may replace this x with z. Okay, so if limit is equal to x and this is less than y, okay, then the limit will be here. So actually, you need to look at this tree. So maybe you can say this is number 1. Okay, maybe this is C. Okay, and this is A. Okay, why I'm putting A and C? So you may look at here. Here's sorry, just need to switch a symbol. Okay, here this sequence Zn is dominated by x squared, and E of x squared is having finite mean, okay, or standard deviation here. Okay, so that means this is, we can have the first conditions, and the second condition is the limit for x squared is equal to x. So I'm just z here. So in this case, so E of x is equal to this, right? So using this, then we can have these conclusions here. Okay, so we can this by this theorem 4.3.3. So we can see this limit of E of Zn is equal to E of Z. Okay, so and because of the probability is 0, okay, so this will be equal to 0. Okay, so this is actually the probability of x is equal to 0. Okay, so this is equal to maybe you can say this is actually equals to P of Z equals to x equal to infinity. So this is equals to 0 here. Okay, so this. So if we come back to here, this thing is actually our Zn. Okay, so Zn is this. We substitute inside. So this one explained. Then this is how we can get it. So we substitute all. Okay. Yeah. Or symbol back to Zn. So you can see this limit of E of this. What is okay, you substitute, then you can get these things already. Okay, this xn is equals to 0. Okay, and you substitute everything back into it, so you can get an x squared 1 of sigma squared of n greater than xn is equal to 0. Okay, these two are the same. So this is how we can get this is equals to 0. All right, so
is it so is it necessary to go through all of these proofs? Because I feel that the fact that an eventually goes to 0 is obvious enough. Yeah.
Actually, it's not that obvious. It's not. You mean this?
Yeah, first, as like n increases, because it's not. Yeah, as n increases, it's going to reach infinity, and so, you know, you're not going to get an x that can ever be larger than that. So that's going to the range of the domain in which x can take is shrinking.
You may say this is obvious in the sense that this is actually not that obvious in a way. First of all, you must have this this hypothesis first. Okay, in the first place, okay, when the variance of x is infinity, so this might not be true anymore. So that's why it's not that obvious that what you have said just now. So that's why it's actually this is what we want to do. You have to verify rigorously, step by step, see whether each of it fulfill all the steps or not. We have to verify each of the procedure carefully. So you say obvious is because of we have made such assumption. This is not infinity. Okay. In fact, if you remove these conditions, okay, if you remove this variance of x is infinite, if you assume variance of x is infinity, so this might not be true anymore. We don't know whether this is true or not.
Yeah, actually, okay,
yeah. Okay. Yeah. So so actually, maybe this is the purpose for the course. Okay. Yeah, I know. We are all persons. Yeah, usually, a person would not analyze a situation in this way. Okay, it's not so detailed as this. Okay, usually we will look at it looks like this. Then we just direct. Okay, this is one of the purpose for this course. So we maybe the purpose for this course is let you have such experience or to let you know sometimes before you apply certain formula, you really have to be ensured all the hypotheses or the situation are fulfilled, the hypothesis. Okay, what I mean is all the hypotheses are fulfilled before you applying the formula. Okay, sometimes it looks very obvious. However, if one of the hypothesis is not fulfilled, and then the formula might not be applicable anymore. Although in most of cases it is true, but you know, there is always some exceptional case. So that's why from the perspective of scientific research or analysis, so we have to be very rigorous and careful. Yeah. So that is one of the purpose for this course. So that's why I want to give you guys have such an experience. So before applying something, so you have to verify things step by step properly. Okay. So for example, this before you need to go to this, right? You have to make sure it fulfills the hypothesis for this dominated convergence theorem. There is this condition C, limit for x care is x, and condition B, x care is dominated by y, and whereby y belongs to L1, which means in this case, the mean for y cannot be infinity. So have to be like this, right? Okay, so so another example. So actually, it's theorems. So let's look at this. So again, we have some consequences of this Lindeberg conditions. Okay. Again, this is actually a quite useful results. Okay. So we have some consequence for this Lindeberg conditions. Again, we make standard assumptions. First of all, we always assume this is independent, right? First, we always assume this is independent. Secondly, we assume the mean for xi is 0, okay, just to simplify our formula. And also, number 3, we assume it satisfies the Lindeberg condition, that this will converge to 0 in probability, and this random variable. This is not right. You make it different. Okay, so the first one is a random variable. The second one is actually a scalar value. Okay, just a sequence of numbers. So that's why this will be converged to 0. Okay, let's look at. Okay, let's look at the first one. Yeah. So again, we suppose the Lindeberg condition is satisfied. Okay, we suppose this. We assume this is always to limit of n to infinity of we summating I e of this xi over sigma n square. Okay, we assume this is always equal to 0. So we want to show that this one converges to 0 in probability. Okay, so what we can do is we can use the definitions. We consider arbitrary positive number epsilon. So then we look at that. So the probability of maximum of xi, I running from 1 to n, follow this, greater than epsilon. Okay. So again, so this is like I said, this is maximum. So the rho is same as the supremum. Okay. So follow what we have observed in the first part. So this actually is equals to P of the union of I is from 1 to n for this larger than epsilon. And no, we know this is a union by using the Boy's inequality. So this is always less than the summating of I of this, P of this. So xi epsilon n greater than this. Okay, so and we know this can be written as this summating E of, okay, maybe I'll put it down here easier. So this is equals to this the indicator function, so xi. Okay, so this is equals to this. This actually by, remember, we have this E of 1, the indicator function. So this is just P of kn. So we have this. And next, this one, we can directly see that. So this will be always less or equals to this. 1 over epsilon square E of this. And again, by our hypothesis up here, so we assume this is equal to 0. Okay. So that's why when n to infinity, so this will be 0 when n approaches to infinity. So from the definitions, then we can see that hence, so we have this limits of P of this maximum of I, so these things, xi sigma n greater than this epsilon is equal to 0. Okay, for each positive epsilon. Okay. So then by the definitions, so by the definitions of convergent distributions, so these things will converge to 0 in probability. Okay, so this is how we can get this proof here. Okay. So for the, yeah.
How come you don't use soup here?
So, which one? I think this is from the questions.
Oh.
Okay, it's like this. That's a very good question. Okay. So just a remark for you guys. Okay. So when you consider only finitely many items. Okay, when you consider finitely many items. Okay, so again, finite, so not up to infinity, then maximum can, you may assume this is equals to supremum. They are the same. All right. So for example, you don't have to worry about it. So for example, if you set a supremum of x1, x2, x3, that's it. Then they are the same. Okay. These are the same. When you consider finitely many items, that's it. So, but when you look at up to infinity, x1, x2, x3, dot, up to infinity. So then we don't know. I put a question mark here. So it could be equal, but it might not be equal. Okay, so in this case, get it? So in this case, I'm actually consider n of them. So this is actually I'm using a shorthand. So I is 1 to n. So that means I consider n items on it. Okay, so that's why doesn't matter. I'm using maximum or supremum. Okay, so unless you consider up to infinity, you may replace this maximum with sup. Doesn't matter. Okay, so for the next one, the proof is given. So I think I can leave it to you, right? So maybe just briefly look at here. So this is a proof for the second case. Okay, so let's verify it one by one. Okay, so for the first line, if you look at here, variance xi over sigma squared. Because of the mean is equal to 0, then we have this. I think this is no problem. Okay, so this one quite straightforward, right? So just put it here because of e of xi is equal to 0. So this will implies, how should I say, variance of xi will be equal to e of xi, no problem, right? Squared. Okay, this one can be split into two terms. I think this is clear. So you can look at here. These two are the partitions, right? You can consider two partitions over here. So that's why you can split into two of them. All right. Okay, so this is the case. So next. So this is always less than epsilon square. Okay, maybe I can explain this later. The second terms remain the same. Okay, so the second term remain the same. Okay, so then this is always less than this. Then the maximum of it must be less than this because of okay, I'll go through it one by one. Okay, so there are two things that maybe we need to justify for over here. Okay, one by one. So maybe just look at part 2. Part 2 is easier. Okay, number 2. This is like that. So let's say you look at here instead of this, right? I'm just saying this. So let's say okay, let's say you have this. You have what symbol I should use? Okay, maybe I use this omega 1 less or equals to n1. Okay, omega 1 is less than n. Right? Omega 1 is less than m2, and omega 2 is less or equals to m2. I think forget it. Make things easy. This is quite simple. Just give you an example. You can see. So first of all, you can see. Let's say 2 is less or equals to 5, right? And 3 is less or equals to 15, right? And 10 is less or equals to 20. Am I right? So you just look at these three. This. Okay. So then you can see, I think it's quite obvious. Maximum of 2, 3, 10 is less than actually 15, right? So it's less than 15, right? But this thing is less than, you just sum all this thing up, 5 plus 15 plus 20. right? So that means you can see this is 2 less than 5, 3 less than 15, 10 less than 20. So that means if you look at the maximum of 2, 3, 10, this must be less than you are adding all of them. Okay, because this must be maximum of them must be less than one of them. So you just adding it must be this. Okay, so this is how you can get it. So this is the second part, is quite easy. So the first part, why this is less than epsilon. Okay. So the first part, okay, again, why? This is actually we have. Okay, why this is less than epsilon? Okay, so if you look at this indicator function, okay, this is square here. You look at it. So you look at this range, this random variable is less than epsilon. So inside within this domain, this is always less than this. So that's why when you multiply this must be always less or equals to this epsilon. Okay, because of this is within this domain. So this is always less than this. Okay, likewise, then you square it, then must be less than square of this. And this is with an indicator function. When you put an indicator function, that is sort of like part of your epsilon square. So that's why this must be less than epsilon square. Then you can see this is how we can get it. So the epsilon, the expectation value for this must be less or equal to E of this. So that's fine. This is less than epsilon square. Okay. So I think once you can get through these two parts, why the first part is less than epsilon square, and why the variance less than this, the maximum must be less than this. So the remaining will be the standard things. Okay. So if you can get through this, so you should be able to understand the solutions for or the proof for these theorems. Right. So this theorem. So just give you a remark here. So in this theorem, what do I have? Here 5.4.5. Okay. Actually, you just look at 5.4.3. Yeah. Yeah, 5.4.3. In this, it said that if xi satisfy Lindeberg, okay, implies that maximum of variance of xi over sigma n square will converge to 0. Okay, so this same. Oh, of course, we do have some other conditions with some other hypothesis, like their independence with some other standard hypothesis. Okay, I just put it here. So we have this. So this one implies this. When this is not true, then you will get this. So we have this. And maximum of this does not converge to 0. Okay, then we can say xi does not satisfy the Lindeberg conditions. Okay, so that's why this is one of the very interesting feature for these theorems. So we actually can use the reverse for these theorems just to verify these conditions. If these conditions fail, then we can say F does not satisfy the Lindeberg conditions. Then in this case, then you be careful. You have to be cautious before applying the central limit theorem. Okay. Okay, so just to give you one example so that we can have this kind of a picture. So I think the calculation should be quite straightforward. So I don't think I need to go through the solution. I mean, maybe just look at it very briefly. Okay. Right. Again, we have to fulfill other hypothesis. That is, first of all, have to be independent. Okay. Secondly, mean must be 0. Okay. Independent. Okay. Actually, we just need the first I. I just need the first I. So can I have a smaller? I just need the first I only. Okay. Independence and 0 mean. Okay. Then next, we just need to verify this. So this is our Zi. So we define Xi to be this. Then I think this is straightforward. You just take the variance for it. So I think this is quite easy because you can see because of I think it's the calculate E of x squared will be just E of 2 power of I and then Zi square, right? So that's why this will be equal to 2I multiplying 1 because the variance for Zi will be 1. So this is how we get it easy. So after that, I think this is just resubmitting, we get this. Okay, so I think maximum of them must be 2 power of n, right? So because of yeah, this is easy. So then this is 2 power of n. Then you can see this one, the limit for this will be 1/2. So which is not 0. Okay. So when this is not 0, the limit is not 0. So Lindeberg conditions is not satisfied. Okay. Okay. So we have gone through several examples regarding to this Lindeberg condition. Okay. Now we can state this condition here. Okay, we can just directly come to this. Okay, let's look at it one by one. Okay, now we can look at our next version of central limit theorems. So the Lindeberg-Farrer central limit theorems. Again, we have several hypotheses here. Okay, first of all, we just require to be independent. Okay, not from the same distribution, all right? Just independence. Okay, not from the same distributions. So that's the reason why we want to consider another hypothesis. Okay? When xi not from the same distributions. Okay, so again, so this is a technical just to simplify the formula, and also we need the variance to be finite, and also it satisfies the Lindeberg conditions. Okay. maybe just one. Okay, 1, 2, 3, 4. Okay, then we have the central limit theorem conclusions. Okay, so they look at here. In practice, Lindeberg condition may not always be easily to check. I think you guys can see, right? So because of the condition is a little, quite difficult. So that is actually we are checking things like that. I think I don't have to state it out here, so you can check it out. So it's not easy to be verified. Huh? So alternative condition that implies Lindeberg condition and which are easy to check may be used. So we look at something that is slightly simpler than Lindeberg condition and also stronger than it. So that is better to be used. So the one of the condition that we can use will be this Naipolov conditions. Okay. What is this Naipolov condition? So this is the one. So comparatively, this is much more easy to be used. So this Naipolov condition will be this. First of all, the third moment not infinity, and limit for this is equal to 0. So this is so-called the Naipolov conditions. So then we have this result. So if you have an independent random variable, again 0 means, and again let's say the variance is finite, and if satisfy the Lindeberg Naipolov condition, then we have this. Okay. So this is actually from our proposition here. Anyway, we are not looking at the proof for this thing. So just to let you know that. But anyway, don't worry. In exam, I'm not going to test you about the Naipolov condition. So this is just for your extra knowledge here. So not tested in exam for these Naipolov conditions. Okay, so you don't have to well, you prepare your exam, you don't have to look at these Naipolov conditions. Okay. Okay. All right. I think maybe I should stop here now. Okay. Maybe before we stop, just go back to the early beginning. The beginning. Just the summary once again. Here's our summary. Okay, so this is the summary. Okay, so in this section, we just focus on the central limit theorem. Okay, so just forget about this part. Huh? Okay, so what we want is under what hypothesis we can apply this central limit theorem statements. Okay, so here we consider 3 different hypotheses. Okay, so the first one will be the easiest one. When all the xi are independent and from the same distribution, okay, then we can directly apply the central limit theorem statements. Okay, this is the first case. The second case is if our random variable are not from the same distributions. So what we can do is we can replace with these Lindeberg conditions and finite mean. Okay, so these two. Having these 2 hypotheses, we can also make this conclusion of central limit theorem. Unfortunately, this Lindeberg condition is a little bit complicated. Okay, if you can go back to here, how this looks like. So you can see, where is it? Okay, so this is the one. Yeah, so we have to consider limit, we have to consider summation, we have to consider indicator function. So it looks looks a little bit complicated here. Okay, so we may replace this with something that is slightly simple. That is the Lyapunov conditions. So this is our Lyapunov conditions. The third moment is not infinity, and the limit for this is 0. Yeah. So that is here. Alternately, what you can say, you may replace this Lindeberg condition with this Lyapunov condition, because this is always implies this Lindeberg conditions. Okay, so if we have this hypothesis, Lyapunov is satisfying Lyapunov condition and having finite variance, okay, then we can have the central limit theorem statements. Right, so that's a summary for the main result for these sections. Okay, yeah, I think I should stop here now. Okay, you have any questions? No? Okay, then I will stop recording.